All right, today we're going to go over section 5.4, which is the definite integral and its properties. So if you remember, we learned about the derivative and then we learned about its application. And now we're going to be learning about the antiderivative and its application. So trying to get my tools to show up there. So if you remember, the derivative is the slope of the tangent line or the instantaneous rate of change. Well, the antiderivative also has a meaning, and its meaning is it's the area underneath the curve. So it's the accumulated amount of change. This right here is the numeric antiderivative. It's the accumulated amount of change. So we will get into the application of that in the next unit. So first, it's talking about how we can estimate this using what's called Riemann sums, which is essentially drawing rectangles. So if I want to figure out the area of this, I could draw rectangles and figure out the area of each rectangle and then add up that area, and that would be an approximation. So that process is called Riemann sums. That's what this scary formula is. And you can do that with the left-hand sum or the right-hand sum. And all that means is if I'm doing a left-hand sum, when I draw a rectangle, I'm using the left endpoint as the height. So I'm going up to the left and going over. That would be an example of a left-hand sum. Whereas if I do the right-hand sum, I'd be drawing from the right over. And so in this case, that would be an over approximation since the function is increasing. So that would be an example of a right-hand estimation. So here's an example. Let's actually compute what the left-hand sum and right-hand sum. It says divide this into 3 equal subintervals. Now, anytime I do these problems, I always recommend starting out with delta x, which is your width. It's the width of your rectangles. The way you find delta x is you do b minus a divided by n. So this is a, this is b, this is n. So 4 minus 1 divided by 3 means 1. This is what you count by. This means I'm counting by ones. So I start at 1 and I'm going to 4 and I'm counting by ones. 1, 1. So I have 3 subintervals. See, 1, 2, 3. Now, if I want to draw my left-hand sum, that means I'm going to go on the left. This is, which one is on the left? 1 or 2? 1. So I'm going to go up to 1, draw a rectangle. And I'm going to go to 2, draw a rectangle. And I'm going to draw to 3, draw a rectangle. I'm going to find the area of each of those rectangles. So my left-hand estimation would be the width of this is 1. The height of this is also 1 for that first rectangle. Use a different color. So then my second rectangle, the width is also 1. The height is right here, which is 2. And then for my third rectangle, the width again is 1. Because they're equal, and then the height is actually at 5. So the area of this rectangle, we add them all together, 1 times 1 is 1, plus 2, plus 5, so 8. So that would be a left-hand sum. If we take the same idea, but we do a right-hand sum instead, I still would be counting by 1. So I still have 1 to 4, I'm counting by ones. But now instead of doing left, I'm going to pick the right-hand side. So I'm going to go here and go over. So my first rectangle is going to be the width of 1 and then the height of 2. My second rectangle is going to be the width of 1 and then the height of 5. And my third rectangle is going to be a width of 1 and a height of 10. So you can see this one's going to be a way bigger estimate. So 10 and 5, 15, 16, 17. So which one is right? Well, this one is an under 1. This one is an over 1, which means it's probably somewhere in the middle. So that's an example of Riemann sums. I'm sorry, I keep yawning so much. Okay. If we did left hand and right hand with this guy, same idea, left hand sum. I'm going to go over 1. So my width is 1 and my height is 10. My next rectangle would be a width of 1 and then a height of 9. And then my last rectangle would be a width of 1 and a height of 5. And so 10 plus 9 plus 5, so that's 14, and 10 is 24. And now since this one is decreasing, the left-hand one is over. And then if we do the right-hand one, instead of drawing from 1, we draw it to 2. So that would be our first rectangle would be 1 times 9. Your second rectangle would be 1 times, you go from the right over, so 1 times 6. And then, wait, hold on. Is that the same graph? At 3, we're at, but it's 6, and I drew that wrong. Maybe that was supposed to be 6, and I think I drew it wrong, so this would be 25. I think I just didn't quite see that that was at 6. Okay, so, and then the last one would be 1, and then 1. So 9 and 6 and 1, we got 16. So whenever the function is decreasing, the left one is over and the right one is under. So it's the opposite of the situation we had above. So this is just a fancy way of showing you this is what Riemann sums are, okay? And you don't really have to memorize this formula. It's just showing you that you're taking the heights and you're multiplying times delta x, just like we did. And this right here, this E looking thing is summation. So you're just adding up all those individual rectangles. And so that's what we did. Now, if you take the limit of that as the number of rectangles goes to infinity, then you get something called the definite integral. And that is this guy. So the summation turns into this. It looks kind of like an S, but that's an integral, and it is like a sum. Okay, we're summing up all those little areas from A to B. So let's talk about some properties and like what that means. So this talks about how the area above is counted as positive and the area below is counted as negative. So your notes don't have this labeled. Let's label this A, B, C, D. Okay, so it's a 0 to C, B to D. I guess we'll call this 0. We'll call that D, that C, that B, and this one A. Okay, so what's the integral from 0 to C? So what that means is just from 0 to C would be this area right here. And they said that area is 6.8. What's the area from B to D? So if I'm going from B to D, I'm going to start here. So it's this area here, which is below. So it'd be a negative 2.13, and then plus the C because C is above, and then minus the D because the D is below. And you can just put that in your calculator and get the answer. And then D to C, now D to C, we're going backwards. Hold on, So D to C, now what happens here is it's a negative for going backwards and it's a negative for being below. So it actually ends up being a positive. It's a negative, so this would be negative 4.17, so it's 4.17. And then from D to A, notice I'm always saying the lower bound first because that's how you read it. So from D to A, so here's D and here was A. So you're going backwards. And so what's going to happen is you're going to count everything as opposite. So that's 3.03, this is 2.13, this is 6.8, and that's 4.17. But then going backwards, below is positive. So it would be 4.17 and then minus 6.8 and then plus 2.13 and then minus 3.03. And then you would simplify that only because you're going backwards. You always read this from bottom to top. So here's what's called the properties of the definite integral. So this is saying if I'm going from A to A, the area is 0. That makes a lot of sense because if this is my function and say I'm at some value A and I'm at A and then I say I'm at A Let me see, can I move this guy? Oh man, I don't know if it'll let me move him. I was thinking I can move him. I don't think that has that feature. So if I'm going from A to A, like I'm here and I'm not moving, my area is 0. And then this says if I'm going from A to B, so say A to B is 3, then going backwards, it would be -3. And this is if you have a scalar multiple, you can just pull it out front. So if I know this area from A to B of f of x is 3, and then I say, what's the area of 2f of x? Well, guess what you can say? It is 2 times 3, which is 6. So you can pull that multiple out, put it in front. This is that you can add and subtract them. So this is the sum, integral of the sum is the sum of the integrals. And then this is when you want to find, so say I had something in between C and say that this was 2 and this was 1. I could say the area from A to B is the integral from A to C plus C to B. So if these diagonals match up, you know, you can add them together. So we're going to use some of those properties to evaluate these below. So I'm going to pull out the 3, that's the scalar multiple rule. And then I have x squared dx, and they already told me x squared dx is 124/3. And I have times 3, and so my answer is 124. This one I can break apart and say 21x minus 6x squared. What's x? X is 12. X squared is 124/3. Notice that the bounds need to be the same. I didn't write them, but you have to check that they are the same. So 21 times 12 minus, that would be divided by, oh no, times 2. So you could simplify that. That would be your answer. Same idea here. Let me see those. Okay, there. So again, I can pull apart that and say 2x squared plus 5x. So 2 times the integral of x squared was 124/3 plus 5 times the integral of x, which was 12. This one I could put -3 in front, and then, oh, notice this says 1 to 6. So that's a little different. I'm going to have to write it from 1 to 5 plus 5 to 6, because that's what's been given me here. See, 1 to 5 and then 5 to 6. So 1 to 5, x squared, and then x squared. And so I got that this part, so this is where we can add these together because these guys match up. So if I know 1 to 5 is this and 5 to 6 is this, I can add them together. So it's going to be -3 times 124/3 plus 91/3. And so what is that? 215/3 times -3. So then it's -215. Okay, so that's adding up the integrals, that property. So that's it for the introduction to the definite integral. We're going to talk more about how to find it exactly next time. So attempt your homework, and as always, please let me know if you have any questions. Good luck.